Test 1, 2.
Become the hecklers. Yeah, you front row. Front row. Either front row or last row, right? That's the only way. That's fine. All right, let's get going. Everyone can hear me? Okay, good, great. I can hear myself now. All right, so this talk is about HBase sizing. Some ideas and thoughts I collected over time, over the last couple of, say, years, running HBase clusters. So I'm hoping that you will be able to take some information away that will be useful if you think about or are already using HBase. Quick one about me. I'm Director EMEA Services, so I was a solution architect for Cloudera and now running the solution architect team in Europe. So we have those specialists that come on site and help come to terms with anything around Hadoop, be it Hadoop itself or be it HBase or anything in between. I'm also, sorry for the suit, I have to apologize. That's like a developer. I'm a developer at heart, so I have Karma in HBase and Weir, so I'm a committer there. And I'm also had the opportunity to write the O'Reilly book for HBase. So if you, everything I'm talking about right now is not in the book. So that's a good information. So if you want to know about the rest of HBase, that's the book. And I'm not talking about new stuff that I've sort of gathered lately. And when I'm sort of proposing right now a refresher for the book, and I will add this information. So there will be sometime there will be a new version. So HBase sizing, that's sort of, as I said, what is HBase sizing? And then to me personally, over the years, I've found there's two things. For starters, you can't just take HBase and compute what you need, because if you do it wrong, you have to use, say, 50 nodes, and it works. Say you get it to work, but you could have done it in 10 nodes as well because you're just using it wrong. So there's two things about HBase sizing. So to optimize HBase sizing is getting it right on the HBase side, using HBase properly, and on the other side, what can a cluster, well, what should I expect from a cluster? So I have some numbers, some examples for you, how to roughly, say back of a napkin, do a calculation on how many nodes do I need for my workload. But you need to hear the other things as well to understand why you would want to watch out for those pitfalls as well, because otherwise your calculations might be way off because you're suffering on another end. So it's two things: understanding how HBase works to a degree, I don't go in too deep, and tweak it the right way, and make sure that you compute then based on that one. Once you have understood and you used HBase the right way, how many servers do you need to actually run a workload? So there's two things in HBase right now, or two major things in that regard, is that there's two reads and writes. They compete for the same resources. As the last line says there, they're really separate code paths. If you look at the code, HBase code, they're fairly separate. They do different things. We look at each separately. But they still do compete for the same resources. So one of the things that you have to look out for is disk usage, I/O. I mean, you should be able to, well, it would be ideal if you would be able to saturate disk, for example, with HBase, which is not typically the case. But disks need to be shared. So there's HDFS underneath HBase, which you have to go through. So if you write or if you read, they all go through the same sort of bottleneck of sorts. You need to make sure that all of these are correct and wide enough not to be like an early on bottleneck. So disk, network I/O. If you have a faulty network, I mean, of course, you will suffer on that end as well. So you have to make sure those resources are sound and you understand them. RPC handlers. There's a stack, or there's a pool of threads on the server side. They take on your requests and they then do the data. There's actually two channels in HDFS. One does the actual metadata operation through RPC, and on the other side you have they're called transceivers. You have the data side of things, but both have a pool of handlers. You have to make sure they are wide enough or large enough. So One of the things you want to make sure is, for example, that you use monitoring, look at these pools, there's metrics for that, they're exported using, for example, something like Nagios, you can see where they're up to. So make sure all of these sort of low-level things are done properly as well. And memory in general. So if we look at memory now, more in detail, reads and writes have to share the same heap that you have given to the Java process that runs the region server in HBase. So you have these region servers are those that do the actual data lifting. So you specify, say, 10 gigabytes of heap and give it to that Java process. By default, there's a split between the write operation and the read operation. So there's a 40 to 20% split given to these two things, and the remainder goes to the rest of the system. So 40% of the heap is set aside to do write operations. That we look at this again in more detail in a second. And 20% are given to the actual reading side. You can tweak that ratio. So again, if you want to optimize your cluster, one of the things you want to look out for is what is my use case? What do I do with HBase? Am I just having a ledger? Am I just attaching data to it? Am I write heavy and only have few reads? Then you can tweak this ratio. So use this to your advantage, so you can see which direction you want to go. And as I said, the remaining 40% go to Java. That is a lot of space as well, which is typically a good idea, but sometimes you can actually take away there as well. I've seen installations where we cut into that 40% that has been given to Java, just to give it a bit more to the write side or to the read side. It makes sense. You need to just look at the metrics. Like anything in terms of graphing is your friend to see where the distribution is, and you can see, for example, from the block hash, what your hit rate is, and so on and so forth. But more on that in a second. So yeah, tweak this to your advantage. Now let's look at each of these separately. So they share the same resources, but what does it mean for each separately? So let's start with the reads. The reads they do a couple of things. When you say something, when your client says, give me a row in HBase, the first thing the client has to do is has to figure out where is the data. So you don't have to do this, it's all done in the client side. You just say, give me a row, and you're done. But behind the scenes, the client has to say, okay, where is that row? Because it's all distributed, right? It's a system that has lots of servers. So it figures out where data is, and once it figured out where data resides, which is typically ranges of data, it caches this information. So that information is something that the client keeps warm. It might get stale, but it will refresh then. You don't have to worry about this. So one of the things you might want to look at, and this is like as a small sort of tip on the side, is when an application starts, you could actually tweak a setting that helps the client to cache a little bit more of this information, so that at startup, you might have a slower startup, a little bit slower startup, but you're caching more information so that once you're warmed up, you can move on faster. So this is this pre-warming or prefetching option that you have in clients. By default, it's okay, but keep in mind, if you think that there's a ramp-up time, can I tweak this? Yes, there's a prefetching that you can tweak a bit so that you can warm up a server, and then basically it's all basically keeping the same performance from then on in. Once it found the region, it goes to that region server, it talks to that region server, and the region server tries to help you out in reducing I/O. This is a vital part of HBase. You want anything in HBase or anything in Hadoop is in the end just physics. So you have disks, you try to get everything eliminated that is slow. Like for example, Seeks. Seeks is a slow operation on disk, so it tries to do a lot of things sequentially. So that's one of those things that is all built in for you, and this is the whole concept of HBase, is to do things, so for example, in a sequential form. But it still has to go out and find data information. The way that HBase stores data is that over time, you're generating store files underneath the system. So as you write data, you get multiple store files. And eventually, it happens that a row that you're talking to, you're updating a row constantly. That row is distributed across multiple storage files on disk. Now, if you end up having 10 or 15 files underneath, and you are asking for this one particular row, the system tries to help you out not to go to all of these 15 rows. and look at, do I have something of this row in here? Do I have something in here? It tries to help you out by using, if it can, hints from the client side. So what you can do as a user to, again, help out the system to be more performant is by hinting information. For example, if you look at data that is only a day old, I only need data from yesterday, tell the system that. There's a time range and you can give it. So that helps the server, for example, to say, oh, he's only looking for data from yesterday, so everything that is older than yesterday, don't even look at those files. Don't even open those files, don't cache anything, don't touch them, don't pollute the OS buffers by opening or doing I/O and mixing things up. Hint this to the system. And the other thing is there's also something like, it's called Bloom filters. You might want to look into that as well. Depending on your usage patterns, the Bloom filters can help you to identify what is where in these store files. They're not really applicable to all use cases. There are some use cases where they don't make sense, especially where you just say, like the ledger, for example, you just attach. But in some use cases where you update rows a lot, they can help you reducing I/O. Again, just you have to read up on that one, but it's an interesting feature. And then there's lastly, when the client then says, or when the region server says, okay, I'm not a region server, so which files do I have to load? But before it goes to that file, it has a block cache. The block cache is this what I mentioned earlier, the read side of the heap that is set aside, those 20%. So it tries those 20% of heap to see if data is already cached in this heap. If it's there, great. Don't even go to that file. Don't even do anything. Return it. Otherwise, then it goes to disk. And that's when the pain starts. Basically, now you're hitting disk. Now you do all of the moving parts. That's the slowest thing. Try to eliminate as much as you can along the way. So looking a bit more into like the block cache. The block cache has metrics. Use those metrics to your advantage. In general, as I mentioned earlier, install a system that lets you monitor what's going on the server side. There's a stack load of metrics that you get from Hadoop and HBase. But all you have to do is memorize a few. Like for example, whenever I go on site somewhere and have to look at a HBase cluster, the first thing I do is I filter the metrics real quick by anything that says, for example, pool, or that says handler. So there are newer versions, for example, of Nagios lets you like wildcard and filter by metrics. So I search for all the handler information or all the pool information, and I go for block cache. I search for block cache. It will tell me how you use the block cache. Do you have like what is it? It's like what's the hit rate? What's the miss rate? How do you churn through the cache? It helps you understanding. Can I optimize by tuning, or is the use case just not worthwhile even touching that? Because if you have a high churn rate, if you do random lookups across the system all the time, the block cache doesn't help you much because you basically have to you pollute the block cache by loading random blocks all the time. The system can't help you that much at that point. So maybe you can switch to a use case, or you can tweak your use case, not use random keys. Maybe use sub keys, like where you have subsets of sorted keys that you get information that you need together. If that is possible, again, you're reducing I/O, you're basically using memory properly, and you need less servers. Yeah, check the eviction rate, check the fill rate. So random reads are not really that good. Tweak the settings, but you can't switch it off. Sometimes people say, well, it's all random, so let's switch it off. That's not a good idea, because the system needs that cache, even for some other information. So the lowest you should go is, say, 10% or something less than that, but you should not set it to off, because if you do that, then every single request that you do, every single get is a disk hit, and that's the worst thing you can do. So keep it low if you don't need it much, but then if you can optimize for it, set it higher. Now the other side, the right side, the writes. That is really sort of the driving factor that I see typically in designing. Most of the clusters I have seen are write heavy. They're more on the right side. They take a lot of information, store them, have a long tail of information. So the reads are more like I read the last few days, like a message store. I read my newest messages, but I never go back and read my messages from like a month ago, or rarely do this. So you have this long tail of information, but you gather and you gather, and users only look at it and just see the subject, flag it as read, which is another update, and then move on. But you don't read the entire message. It's not transferred often, and so on and so forth. So that is a typical system, and that typically drives, as I see it, the cluster size. And there's a few reasons why, and we get into that. The way the writes work is a big table where HBase comes from is using something called log-structured merge trees. That's the idea I mentioned earlier. Try to avoid seeks on disk, because seeks haven't improved lately over the last couple of years. Seeks is the slowest operation you can do on a disk. So instead of going to different places like a normal database in the past typically did with B trees, finding where you have to update information, update it, go somewhere else, you do these seeks and seeks. It tries to do everything sequentially. It writes data sequentially. It basically writes data as you insert into HBase. It does two things. It puts it first into a write-ahead log, just like a bin log in MySQL. It's the same thing. Just a log. It just sequentially, it just appends to the end of that file and rolls it on a regular basis. And then it puts it into in-memory store, in-memory storage, sorted by key, puts it in memory, and keeps there. Then once you have enough in memory, so it accumulates in memory, and then it writes it out to disk. Right? That's a flush. That's what it's called. It's a flush. Writes it out, sorted, the way it was in memory, sorts it, basically pre-sorted, write it out to disk, and then you're done. There's a note here saying that it also does this under pressure. So we get into this in a second. So there's a reason sometimes it doesn't do this at the configured maximum space that you have given it, or that you want it to do it, because you're doing something wrong. Again, we pick this up in a second. Then once it's been written, once it's been flushed out, the old logs are checked. Everything that is in that log, is it everything already flushed out to disk? Yes. Then it's been deleted or kept for replication and stuff like that. But typically, there's a cleanup in the background. You don't have to take care of that, and the logs are discarded eventually. And now, I mentioned earlier that all of these flushes are these files that I mentioned earlier, those store files that you generate, or the system generates for you over time. They have to be compacted. The reason is that you typically don't want to have all of these 15 files all of the time, looking at each of them. Sure, the user might give you a Bloom filter or like a time hint that helps, but typically you want to keep that number to a certain maximum amount. You don't want to have this grow forever. So there's a background process that rewrites these files and packs them together into fewer, larger files. That's called a compaction. And again, there's something we have to look into this in a second. So for write performance, there's a few things that you have to do, you have to keep an eye on. Is that if this drives this cluster size, then you want to make sure you do the right thing on that side. The first thing is that you have to look at the key distribution. Keys, with the row keys, which is like the primary key in a database, for example. If you use that wrong, then you can have a negative impact on the write performance. If you use it right, then it should be mitigated as best as possible. The reason why there's a sort of other systems randomize this key, just randomize and you're done. The problem is then in all of the searches, all of the range scans that you want to optimize for reducing I/O, instead of doing these random lookups, you want to do block lookups, which is much faster to load a block than small blocks everywhere. That's counterproductive. So HBase gives you the option, it's your choice how you design the keys to drive where you write data. If you have sequential keys, like a timestamp, it writes it sequentially, which means you're hitting the same server over and over again. In HBase, a region server serves every region server serves a set of contiguous row keys, and if you keep writing sequentially, you're hitting the same server over and over again. If you do it randomly, you hit all of the servers. So you need to find a balance in between. Sometimes you have to design a system where you get around this by using, for example, bulk loads and so on and so forth, or tweak it in a way that you only do sub-ranges. So that's something that you have to do on the client side. Unfortunately, yet, I'm expecting that to have in the future, maybe third-party toolkits that help you to put this on top of HBase to simplify this sort of operation. But at the moment, it's quite raw. You have to look at how do I write into HBase. If you write everything sequentially, you might not getting the performance you're looking at. You typically, even if you have 1,000 servers, you get the performance, the insert or the write rate of a single server, which is like a cluster of one server. So that doesn't help you. What I mentioned earlier, handlers, keep an eye on the handlers, go to the metrics, look at the handlers, look at the logs as well. Is any mention on the handlers? you need to make sure that this number is large enough or wide enough to not form a bottleneck on that end, so they don't pile up too early on that one. The worst thing that I've seen is typically the write-ahead log itself, and I'll go into this in a second. And finally, the compactions that I mentioned earlier, where it rewrites the files, there's an algorithm to it. There's a few knobs you can turn. If you don't touch it, if you never touched the compaction algorithm, if you run HBase today and you have never even looked at this, there are chances that you actually could improve the whole situation as it is today, or improve your cluster performance by just looking at those numbers. Because a badly tuned setting, or which is the default, could be bad for you, could be great for you, who knows, that could cause a lot of background churn that you would feel the cluster going over like the weeks, it goes slower and goes slower and it goes slower, and you're like, what's going on? It started off so great, and all of a sudden HBase goes slower. That is typically the case. And again, I have something on that one. The write-ahead log now in more detail. So this is the one that keeps the data safe. So if the server crashes, you can replay the log and get all the information so that you don't lose anything that's accumulated in memory. Those in-memory stores, if they have not been flushed to disk, the data would be lost otherwise. So the bin log is important to write to. The problem here is that they store the way the original paper was written and how HBase is implemented. There's only one write-ahead log on a region server. So all of the updates that you write have to go and have a single writer problem. They write to this one file, and depending on what you're doing, this could be your bottleneck as well. So there's a few things the developers work on. One is write-ahead log compression and multiple write-ahead logs. These are sort of been discussed. It's a bit stalled. That hasn't been write-ahead log compression is now in, I think it's now 94 and 094 and onwards. The latter one, there's a discussion of doing it differently, so this hasn't been resolved yet. So, but keep in mind, write-ahead log might be an issue for you. Configuration-wise for the write-ahead log, it's set to 95% of the default block size of HDFS. So typically you run, say, 128 megabyte, 64 is not that common anymore, say 128 megabyte of block size in HDFS. So HBase opens this file and says, I roll this at 95% of that size, which is about 120 or whatever megabyte, and keeps a number of them around because it has to keep them until they're flushed to disk. The number is set by a hidden, that's unfortunate, by a hidden configuration setting to 32 as a max log file setting, and it's set to 32. So you have 32 logs time until basically you're running into this limit where it says, I have 32 logs now, but there's some edits that haven't been written out yet in the oldest log file. Before I can throw this away, I need to write this out to disk, and that's what I mentioned earlier. It causes a forced flush of data that it resides in memory. A forced flush means it tells the system, it's like, if you want to move on, we need to clear out some logs here because you told me only 32, that's all you only want to have. So force the flush. The flush means it didn't have enough time to accumulate enough data to actually trigger the size-based flush. So you're writing smaller files to disk. So you're ending up, when you look at the flush size, you're looking at the files on disk, or there's a log message as well, and you look at that, and you have, say, configured a flush size of 64 megabyte or 128 megabyte, whatever it is, and you look at the logs, and the log says, I flush at 1 meg, I flush at 2 megs. It's like, there's something wrong. That's seriously wrong. If you have like way too small of these flushes, and it will tell you that it force flushed this, you're running into this problem. You have contention between how quickly you update data and how quickly the logs are discarded. So you have a couple of options here. You can either increase the log size, you can increase the size of the log, set it to 256 megabyte, for example, so you keep more around, which cuts into like recovery time if really something happens, but you get more room to breathe. It's better to do that than actually having pressure and doing forced flush. Or you increase the number. There's this hidden setting, you can increase 32. I had in one instance, we set it to like 120. That's what we had to do, because otherwise we wouldn't be able to keep up with the inserts. And you can compute that number, and I have an example on this at the end, based on your distribution and how you fill this. So if you know how much you put into HBase, look at the bytes that you put in, you can compute how quickly you fill those 64 megabytes per region, per server. So you can do the math fairly easy, and I have an example on this one. So there is a further complication with the write ahead log. The write ahead logs basically, they're synchronized not only like for all of the updates for like across the server, they're also synchronized across the stores, and a store is a column family. In HBase you can group columns in column families, which makes sense to a degree. You can't have too many typically, and the reason why you can't have too many is exactly that. Currently they're wired together, which means the problem is that if you update a row, and one row, say, is for example, you have one information that is a message store example. One is an MMS and one is an SMS. The SMS is very small, like say a few bytes, 20 bytes, 30 bytes, with a HBase overhead, maybe 60 bytes. And then you have a video file or an audio file or an image as an MMS, and that MMS is, say, 2 megabyte. Now, because you're going through this single writer there, the 2 megabytes have to be written, and all of the small writes, which are much, much faster typically, they're now piling up in the back. And when you see this, when you look at, we used, for example, Visual VM, and we looked at the threads, the actual handler threads. We had enough handlers, we checked that number that I mentioned earlier, we checked that, looked okay, we had enough handlers, but what happened is they were all green, and all of a sudden all of them went red, they all blocked, and then basically all green again, all blocked, so they go binary, they go like on and off, and it's like, what's going on here? That's because this big write locked up all of the small writes. And so you have to think about, if this is a current problem, because we said we're working on the server side to improve this, but if you have this problem today, you need to work around this. It's the only way. You have to either write in separate tables, or separate regions if you can, or sometimes even you have to switch off the write ahead log usage for example, derived information. We had done this in the past where I switched off that for, we had main table and we had auxiliary tables or information. And I only wrote the main information into the write ahead log, and the other one I didn't. So in case of a crash, I had a coprocessor, which is a server-side code, that would identify, oh, I'm restoring this record, and I would then derive again the information and store it again in the other table. So it's a bit of a nasty one, but it might happen, and this is like the top percentage or so of issues, but keep that in mind. Flushes. Flushes, I mentioned, are when you have the memory filled up and it writes it out to disk. Every operation that you do besides a get or like a scan is really a mutation, like a delete or a put, or an increment, which is a server-side put and get and put. Those are really just what accumulates information on the right side. And when you do this operation, when you do a put or like a delete, the server says, do I have enough? Can I flush now? No, move on. And if it has enough, when the threshold is met, then this data that you have accumulated in memory is being written out to disk as a new file, right? And once it's been written out, it also says, now check if I have to run a compaction. So all of these are wired together. They're all depending on each other. So once the flush is done, then it says, do I have to compact? Do I have enough files? And then the compaction will say, oh, yeah, now I have. In the beginning, it says, no. Now I have like more than 5 or 10 or whatever it is. Now start compacting them in the background. So you will see if you look into like the details of the compaction algorithm, how it tries to optimize this to compact new files quickly to get like larger files, and then you have to decide what you do with the tail. Do I want to compact everything together with a major compaction, or I want to keep this? How often do I run this? So there's a few things that you have to have a look at. The problem here is, when I mentioned earlier, is that if you have this premature flushing, if you have this problem where you run into the number of logs being exceeded, or memory pressure in general, then you have small files being written out. Now it tries to keep up with these small files. There's new small file, and now the reason why you're creating these small files is because of memory pressure, but now you're creating I/O pressure, because small files means more compactions, more rewrites, and if you have tuned compactions wrong, it merges a 1 megabyte file into a 100 megabyte file, and a 1 megabyte file in a 101 megabyte file. So he rewrites 100 megabyte, 101 megabyte, just to get this little bit into it. And that causes a huge churn on I/O in the background, and that can cause these compaction storms that are really causing issues. And the reason why this is even worse is, you remember I said they're all wired together. So all of the column families are flushing together. The problem is, if you have a column family with the MMS and the ones with the SMS, then what you have is basically that you write out this large file. This triggers the flush because this reaches makes up the majority of the flush size, and lots of these small files. So if you have a setup where column families, one is very heavy and others are very small, you need to keep an eye on this one because you're forcing the system to flush out small files, not just because of memory pressure in this case, but because the large family triggers a flush to disk because it reaches memory or reaches the pressure or whatever it is, and the small files, they tail along and they're causing these backgrounds rewrites and they accumulate and causing troubles. These are called compaction storms. So keep this in mind, this can happen. Few dependencies. So as I said, flushes happen across all of the stores, which is all of the column families, and even if it triggers one. So this is what I just said. If you have configured, for example, the flush size to 64 megabyte, if you have this MMS here with 55 megabytes, and SMS, and this could be metadata, for example, 3 column families, then you have this one plus this one plus this one is 64 megabyte. That's the flush size, so this across all of the families, and that now triggers these files being written to disk. So you're writing a file out which is 55 megabytes, 5 and 4. So this is what causes these issues long run. So in this case, you might want to keep the small information in the main column family. Don't have multiple column families in this case. Or keep some, if you can live with it, if your system is fine, if you don't feel that pressure, that's okay, but keep an eye on that. And now we get to like the second half. So I'll give you some numbers now, what I've seen. The typical saying is if you just test HDFS with a pure write a file into it, you see about 35 to 50 megabytes per second write performance because of the replication that happens and all of the other overhead. It's not the full disk speed. That's the first thing. You don't get full disk speed with HDFS yet. We're improving on this. Every version gets better and faster, but there is currently about, let's say, 35 to 50 megabytes per second. If I do the math, if I use a cell size of 1 kilobyte up to like half a meg, and just do the math there, just see how many operations I can do per second by dividing the throughput, you can see that I should be able to do maybe like 70 to 100 per machine, 70 to 100 in a half megabyte range. So if you want to insert like 1,000 of those, you would need to have like 10 servers to really keep up with that. On the other side, if you do the 1 kilobyte, which is typical, what you rather do in HBase is more amenable to smaller key values, like more smaller information, smaller details in the columns. You should be able to do this, which is, and that's why I painted this in red. I don't see this currently. So there's more bottlenecks hidden in HBase. What I really see is more this sort of setup. You can see that I typically see more like 10 insertions for like half a meg. And maybe for 1 kilobyte sizes, I see maybe 6,000. There's one test that Facebook ran on the Insights cluster. They were able to do 1 million updates on a 100-node cluster, so 10,000 per server, and they only did counters, and the counter is 8 bytes plus overhead, so each cell is about, I don't know, say 40 bytes. So they can do 10,000 then. So that makes sense. That sort of is along what I have seen as well, and keep this in mind as if you do the backwards math, you see it's actually 15 megabytes per second you can do in HBase. So don't expect HBase to saturate the disks. I have never seen this really, unless you do other stuff as well in parallel and try to bring it up. But a normal single use case, it's not ideal yet. It's getting better, as I said, but we're talking about a 0 point something open source software. This is not Oracle or not any other specialized database that is optimized for that in C code or whatever it is, using their own drivers. And so this is the userland code. There is room for improvement. But stem off your calculations, your sizing nodes, your sizing basically on those nodes. Right, so quick notes. Compute the memstore size. That's the size that you need to flush to disk. Compute is based on the number of regions, the memstore size is computed based on the number of regions times the flush size. So if you, I'm talking about those 40%. Those 40% of the heap that you give to the mem stores is based on how many regions do I have per server and what's the set flush size. So if you have one region and set the flush size to 64 megabyte, that's what you have to somehow allot to it. If you add more regions, which is more typical because you want to have a distribution, you dilute that memory into multiple regions. And I have a spreadsheet on that one. And vice versa, compute the number of logs based on your fill and flush rate. So how quickly you can churn data through memory when you fill up memory and then write out to disk so that the old logs can be discarded. That is something you should also keep in mind because that all sort of stems together. So it really is driven by the Java heap. So the Java heap, the setting, and you can't go too high because then you get buy into garbage collection issues like general Java issues. The largest one I've seen is maybe like 20 or 24 gigs of heap lately, even with the off-heap caching and things like this. This hasn't been proven yet. So the typical sizes are more like 10 or 12 gigabytes. Yeah, keep an eye on the region counts, because if you do have too many regions, you dilute, you flush too early, and I have a spreadsheet on that one in a second. And look at the key distribution. So make sure that you use all of the servers. That's what I mentioned initially. Let's wrap this up with a cheat sheet. Ensure you have enough and large enough write-ahead logs, so you don't run into the issue that you flush prematurely. Ensure that you don't have oversubscribed the available memory for writes, or 30-40% or whatever you set it to, have enough of that. Ensure that you set the flush size, matching that size, so this all is just simple math. And check the write-ahead log usage carefully, so make sure that you're not bottlenecking on the write-ahead log. Further, always enable, if you can, enable compression. There's pretty much never a reason not to. Maybe if you just store like JPEGs, things like this that are already compressed. But otherwise, think about using any help that you can get from the system. Compression, choose the right compression algorithm. For recent data, use Snappy or LZO. For old data that you don't touch that often, think about maybe using bzip2 or gzip. So you can tweak this basically in different ways. And yeah, you make use of that one. Tweak the compaction algorithm to pack the background I/O. You don't want to have these background I/O taking away your precious I/O. Keep a check on that one. So tweak the compaction algorithms to maybe not compact everything in the background, or top it off somewhere. Consider putting uneven column families in separate tables so you get a distribution, as mentioned earlier. You don't lock on the write-ahead log. And check your metrics carefully. Look at these as a block cache, memstore, queues, handlers, those words, those keywords, and just look them up and then make sure they make sense. So that's the last slide. That's the math now, like really simple. Assume you have 10 gigabytes of heap that you want to give to the Java process. So the machine needs to have at least 24 physically, right? So, but say you give 10 gigabytes to the Java process. Then the memstore by default has 40%. 40% from like 10 gigabyte is 4 gigabyte of heap. That's what you give to the writes, to the memstores. And you 2 gigabytes to the block cache, so it's 20%. Now the desired flush size is typically set to the block size as well, so it's like 128 megabyte. So 128 megabyte, and you divide the 4 gigabyte that you have, you can only really have 32 regions per server. Otherwise, you already have too much, you have oversubscribed the memory. The 4 gigabyte can only fit nicely 32 regions to fill up that memory. Otherwise, if you put 100 regions on it, then they might pollute this. Keep in mind, these are active regions, not the number of regions. You can have 1,000. If they're not using the memory, they're not occupying any memory. I'm talking about 32 active regions that are currently being written to. The rest, the idle ones, we don't really care about. For the write-ahead log now, it's 95% of 128 megabyte. So and divide this by the memstore size, you're ending up with about 32 partially uncommitted logs. It takes 32 logs to flush everything that is in memory until this has all filled up. But you remember, it was set to 32, right? So you're getting now just to that point where it sort of hits the sweet spot. So you might, sometimes, you can see this in the logs. If you look at your logs, you would sometimes see it saying, oh, I prematurely flushed, but it happens only like once every few days you see that log, or once per day. That's fine. If you see it constantly, you're completely over there. Like you're on the wrong side of that equation. Now, if you set the region size, that's the actual size before you split a region and further distribute the system. If it's set to like 20 gigabytes, which is more common today with the latest version of HBase, 20 gigabytes is a usable size. In the past, it was like 1 gigabyte, which was really small. But say 20 gigabytes. So if you do 20 gigabytes times the number of regions you can have active, so you have 32 regions, So you end up with like 640 gigabytes really of raw storage in use at the moment. Sure, that doesn't count the other regions that aren't in use, but you can see there if you have a server with I don't know, say 12 terabytes of data, that server might already have way too many disks to really use them with HBase. So you have like a replication factor. So, but in general, a Hadoop cluster is more than sufficient for HBase, unless you have not enough RAM. But overall, if you only use HBase, you might want to have more servers to get better distribution with less disks. You get only 6 disks per server, but more of them, right? So distributed on the hardware side. That helps you getting all of these more handlers, more logs, everything breathes easier. Don't get 4 or 3 heavy, or say 5 heavy machines. Rather get 20 machines that are much smaller of spec, but you get the distribution. Right, any questions? Only have a minute or so. Where are the hecklers? Here we go. Freezer.
Just a question about the HBase performance numbers
Yeah.
in relation to the other numbers. Do you assume these days that you're using the local write
Yes.
trick?
Yes. Yeah. Yeah.
Your HBase user is
Yeah.
user that combines
Yes. Yes. So the question was if there's now a feature to bypass local writes straight to disk, so your reads, so you can actually bypass the HDFS process, the data node, and that's already switched on basically. But that number really, using local writes helps you in the performance on the performance side, but it doesn't make a big difference because the big difference is the bottleneck, the single writer issue. If you were to parallelize this, then you would make use of the actual I/O. Here you're actually backing up on Java side things, on I/O things. So that's the big issue at the moment. Yeah. Yeah. Yeah.
So you gave us good rules about configuring HBase, but how do you have rules for configuring HBase running with HDFS?
Yeah, good question. So what do I do with mixed workloads if I use HBase with MapReduce, the canonical use case? The canonical use case is HDFS for the web crawl, or HBase for the or Bigtable for the web crawl, and then using MapReduce to do the link computation for PageRank. If you do that, I typically start off with a very low concurrent number of tasks. So if you have, say you have 8 cores, 8 cores with hyperthreading is 16. We typically oversubscribe that number to a few more. We typically would say run 20 concurrent tasks on a machine. That's what we would typically configure on a normal machine. With HBase, you would kill HBase right away because you have like 20 threads reading from HBase, and they all go through this bottleneck. That's just instant death. So what I typically do is I go the other way. I go with like 1 or 2 threads, concurrent ones, for this particular workload, and see if I can increase a little bit more. So I come from the complete other end, run with 1 or 2, works, good enough, leave it there. If you can go with 4 to speed it up a bit, okay. The worst thing with HBase is it doesn't have a graceful degradation. So if you overdo it on the load side, HBase just dies. It falls over like a stack of dominoes. That is not a bad thing. It's just that when you need to be aware of that. You have to protect your resources. You can kill any other process as well. It's not like HBase is bad. It's just that it would be nice if you overdo it on the MapReduce side, that it would actually then sort of like throttle you back. But that is not built in yet. So that's something that I would love to see there as well. And then in terms of resources, you want to have more memory, right? You want to share the memory. So HBase is a memory hog. You want to get at least 10 gigs. So if you have MapReduce needs for every thread that you spin up needs some memory. So you typically then start with machines with, like, say, 48 gigs of RAM. Disk-wise, as I said, 8 or like 6, 8, 12, whatever disks you have, are just fairly common today. That's fine. I mean, we don't have to do anything on that end. It's really just more memory so that you balance this right, configure these things right, and don't overdo it on the MapReduce side. Because otherwise, you really just, as I said, you stress the system so much that it actually keels over. Anyone else? Otherwise, I'm around, so if you have more questions, want to chat HBase, I'm up for it. Thank you very much.